All right, all right, all right. Hello, everyone. We are down to the last stretch, um, home stretch, I guess. So there's maybe one and a quarter lectures on nonlinear systems, nonlinear solvers, and then we'll hit ordinary differential equations. I hope to cover everything in ODEs because last lecture is April 26th. So that's gonna come up pretty fast, 5-6 more lectures. And then, we'll part ways. I'm gonna miss you all. So I'll see you on the final exam, okay, which will be in the same spirit as exam 2. Everyone did so well on exam 2. I don't have the statistics. I'm not sure if you can see them, but I'll share them on Thursday. But as far as I've seen, everyone was happy. I've even had email compliments. Thank you so much for a great exam. It's like, yes. So, and it's when teaching and trying to evaluate yourself and others, and as a teacher, like, what is the best way to check whether you learned what you're supposed to learn, whether the objectives were met. It's not to punish you, right? So sometimes teachers might get in the mentality like, yeah, we need to test them on this, and if they don't know it, they're gonna get 0. That's an unhealthy way to teach. So that's why I think kind of the 2 or unlimited attempts, I think they have value in them, especially to test this high level knowledge. And I think I'm taking the course in that direction. Your homework assignments are going to be, heavy on programming, heavy on the technical skills, right? But the exams are more on the general understanding, which could be as hard as the very technical math level understanding. But so anyway, I'm hoping this will pay off. We'll see in the next few years during your exit interviews or other courses how well you're going to be doing on those ones. I apologize, I have not posted the previous 2 lectures on nonlinear equations yet. I will post them today. And today we are gonna try to wrap it up. I hope to finish everything today. If not, we'll leave a little bit for Thursday and we'll start on ODEs. So, so far with nonlinear equations, we dealt with a single equation, okay, single unknown. Solve sine x plus log x equals 0, okay? Or sine x plus log x equals 5. You write that in residual form, put everything on the left-hand side, for example. So sine x plus log x minus 5 equals 0. That's your residual function. And you find the value of x that makes that equation equal to 0 and essentially intersects that curve with the line y equals 0. And we looked at closed domain methods, essentially the bisection method primarily, and then the regular falsy method, where we bracket the root and we home in on it. And then the most popular method that we talked about was an open domain method, Newton's method. We derived that for a single equation. Today, we're going to derive it for a system of 2 or more equations. Visually, to visualize the roots for a system of nonlinear equations gets much harder very quickly, because you run out of dimensions on a plane, on a paper. You run out of dimensions to visualize that. So it'll be harder to visualize, and that's why bracketing methods are harder to implement in multiple dimensions, but they're easier. But open domain methods are easier because you can just take a guess where the root is and let Newton's method try to find it, okay? So first, I'll start by giving an example and asking the question. So here are 2 functions, half x cubed plus y equal 4x and y equals sine x. There's a typo here. This should be e to the minus x. It's corrected on the subsequent slides, so don't worry about that. Okay. That again. So these are 2 functions, okay, half x cubed plus y, and we're lucky enough here to plot it on a xy plane, because you can extract y. You can write the first equation as y equal 4x minus half x cubed, and the second one is y sine x e to the minus x. So you can plot them on y versus x plane, and you see these 2 curves, okay? One of them is in the black line, and the other one is in red. So now the question, what does it mean to solve a system of equations looking at this graph visually? What does it mean to solve these two equations together visually? Alicia? Pardon me. Okay. What were we? Oh, was it Paula? Intersection, yes. So both of you are correct. So it means finding the points where the two functions intersect each other. Okay. In other words, it's these points on the graph over there. Okay. It means finding those points where the curves intersect each other. Exactly that. Okay. Now, when you have the two functions like this and you cannot extract y out of it, it's going to be really hard to plot the functions. So I chose this example specifically because it kind of simplifies the illustration. But once you get to more complicated nonlinear functions, it's really hard to make plots like this. And when you have more dimensions, x, y, z, and other independent variables, there's no way to visualize those cleanly. Okay. So we're going to apply Newton's method for systems of equations. And what I'm going to do first is actually show you how we solve this in Python, show you how easy it is. So we have a tool with us to check and validate our solution methodology as we derive Newton's method. Okay. Now, the first step is I want to write these two equations in residual form. So go ahead and write them in residual form. The residual form said you move everything on one side and define that as your residual function. Okay, so you're going to have two residual functions here. Call them R1 and R2. Okay, and just write them in residual form, just like we did last time. It does not matter whether you move things to the right-hand side or to the left-hand side, because you're going to set those equal to 0 anyway. And that will be the equivalent of multiplying by a -1. Okay. Yeah, so this is e to the minus x. That's correct on this slide. X, okay. Yep. Okay, so let's see. What I got here is the first equation. I defined the residual function for it as R1, and I moved the 4x to the left-hand side. So R1 is 1 over 2x cubed plus y minus 4x. And then for the second function, I also moved to the left-hand side, y minus sine x e to the minus x. That defines R2. Okay, so now solving this system with R1 and R2 now means finding x and y such as both R1 and R2 are equal to 0 at the same time. Nathan. What do you mean y positive? It doesn't matter, because once you set them equal to 0, you can multiply by a negative sign. So it doesn't really matter. So now when you recast in terms of these residual functions, now what it means to find the roots is finding x and y such that both R1 and R2 are equal to each other and equal to 0. Those are the roots. Now, before we derive Newton's method for systems of equations, I want to show you how we solve a system of nonlinear equations in Python using fsolve. Okay. So thanks. Question on Zoom? Was there a question on Zoom? If you're not asking a question, please mute yourself. Okay. So thankfully, fsolve can be used to do a single equation with a single unknown, or 2 or 15 or a million equations. Okay. It will do that. It doesn't matter. We just need to learn how to pass on the information about the system we're solving to fsolve. Okay. So in general, you're going to be given a system of residual functions. I'm kind of jumping the gun over here, but think of R1 and R2 with x and y that we had. That can be generalized to an arbitrary number of residual functions, as long as there are as many residual functions as there are unknowns. So you have 5 unknowns, x, y, z, t, and w. Then you got to have 5 residual functions. Otherwise, you cannot solve the system. It's going to be either overdetermined or underdetermined. Okay. So I'm assuming I have as many residual functions as there are unknowns. I'm calling them here R1 through Rn and X1 through Xn. So these are the X, Y, Z, or when you remember nonlinear regression, they were the coefficients alpha and beta, or in the Kmax and Cs in the bacteria example. Okay. So once you have that system, you need to define the vectors, the vector of residual functions, which is just simply a list or a NumPy array of residual functions listed in the order you intend to list them, R1, R2, R3, R4, etc. And also the vector of solutions, which is X1, X2, and Xn. Okay, because fsolve, just the same way it takes a single function with a single variable, is going to take a vector of functions with a vector of variables and return a vector of solutions. Okay, it's pretty neat. So how does this work in practice? You would define a Python function that takes a vector as argument and returns a vector of residual functions. So let's take this example that we just did. We had R1 and R2. R1 is 1/2 x cubed plus y minus 4x, and y minus sine x ex. Then I define simply a function called residual, or my residuals, whatever you want to call it. And I'm assuming that this one takes a vector valued array, the x values. Remember, we're going to pass x and y to these residuals, right? So internally, the Newton solver that fsolve uses needs to repetitively call this residual function to evaluate. It goes and solves for x and y, and then passes them on to R1 and R2, evaluates, checks for convergence, and then keeps iterating. So this x vals over here is actually an array of vector of numbers, x and y, or x1, x2, x3. So what I'm doing here, by definition, I intend to mean that the first entry in x vals is my x, and the second entry is y. Okay, so x vals 1 is y. And then I define my residual functions, R1 or F1, that's 0.5 x cubed plus y minus 4x. And then my residual function 2, R2 or F2, it's y minus sine x e to the minus x. Now, this residual function needs to return an array with containing R1 and R2 that we just evaluated. Okay? This is technically in programming called the callback function. That's the function that fsolve is going to repeatedly call back and forth to evaluate how well it's whether it's converging or not. Okay? And when it calls that function, well, that residual function is a system of equations. So that system of equations, to fully evaluate it, you need two values, x and y, right? If you had 3 equations, you would need x, y, and z, right? Or x1, x2, and x3. Okay. So once you do this, that's the only step you need really to use fsolve. You just need to define your residual functions. Okay. Once you define that, that's it. You simply call fsolve. You give it the name of your residual function, so residual vector, and you give it a vector of initial guesses. Okay. So for this case, for example, fsolve, I'm going to call this residual function that I just defined. And I'm going to start with an initial guess of x equal -2 and y equal -1. That's all there is. If you had 50 equations like this, 50 residual functions, you'd have to program them. They might be programmed with a for loop, for example, because they might look similar to each other. Or you might have to hand type them, and that's fine. But that's all you need to do. That's it. And you can use fsolve. Okay? So grab a Jupyter notebook, and let's do this together from scratch. So this is my notebook. I'll zoom in a little bit. And nonlinear systems exam. Okay. So I'm going to import my boilerplate stuff. Okay. And I'm also going to need sine, cosine, and exponential. So I'm just going to import them from NumPy. Import cosine, sine, and exponential. Okay. So if you don't have a place where you copy and paste this, just take a minute and type it up. You all see? Yeah. All right. So first thing I want to do is plot the functions that that I have, but just for this example, we were lucky enough that y can be separated away from in each equation, so we can do a y versus x plot. Okay. So for the first function, I'm going to define. Actually, here's a little trick using lambdas. If you haven't seen this, or have you seen lambdas in Python yet? So look at this. This is a little tangent, little trick that you can use for defining functions very quickly for simple functions like this. It's kind of annoying that I have to write define y1 of x and then do a return of 4 times x minus 0.5 times x cubed, right? So you can do this by saying y1 equal lambda x, okay, equal 4 times x minus 0.5 times x cubed. So this one is identical to that one. It's just a shorthand, okay, for doing a full defined function. Now you can call y1 of x later, okay, and it's a fully returnable function. Use either one, doesn't matter. Lambdas are a very powerful concept in programming. They go much beyond what I'm illustrating here. So I'm going to do a lambda also for the second function, and that is sine x times exp minus x. Okay. Now, my objective in defining these functions is to actually plot them. So to plot them, I'm going to create a linspace from minus 4 to 4 with 100 points. And then I'm going to do a plt.plot of x, y1 of x, and then x, y2 of x. Okay, and then plt.grid. Okay. So take your time. When everyone is typing, sounds pretty cool. There are some keyboards with some of the older IBM keyboards they used to have. They were spring loaded, so they sound pretty loud, and some programmers really like that. I liked it for a minute, for a while, but then my colleagues, it was very, very noisy until I ended up sitting next to a colleague who had one of those. I mean, they're really expensive. Like you go purchase them. I found one at Desert Industries once, but they're very loud. It's like worse than the the airport the counter. Okay, so if you've got this, then this is x on the x-axis, y on the y-axis. Then we know we have a bunch of roots. We have a root here, root here, root here, and a root here. Okay, and we're gonna try to find all of those roots. Okay, the Newton method or fsolve is gonna find only one root at a time. Okay, all right, are we good? Okay. Thank you for the feedback. All right. So now we're going to define our residual function or residual vector. So I'm going to call it residual vector, let's say. Okay. And I'm going to assume it's going to take a bunch of x values, like I said, x, y. So always document this. X is the first entry in x vals, and y is the second entry. You can invert that definition, doesn't matter. But as long as you are consistent in your ordering, okay? In the meaning of what x and y are. Okay? So simplest thing I do is say x equal x vals 0 and y equal x vals 0. Okay? 1. Now I define R1 just like I did in the code and the slides, which is 0.5 x cubed plus y minus 4x. And then R2 was y minus sine x times exponential of minus x. And now I'm going to return a NumPy array containing these two residual functions. You can return a list, you can return a NumPy array, be just fine. Okay. And this could be a NumPy array or a list also, it doesn't matter. Okay, because we're not needing any NumPy work being done here. Okay. Okay. Give you a few more seconds. Okay, are we ready to do an fsolve on this system? Okay, which root should we try to find, Alicia? Let's say, which root do you want to find? Like this one? Yeah, okay. So this one, I'm gonna try to, because I've seen it, right? I'm gonna try to give it a guess. For x, I'm gonna start maybe -1, and for y, maybe -3. Okay? Sorry, -2 and -3, or -1 and -3. Okay? So this is what we're gonna do. So this one we evaluate, and then we simply call fsolve. Okay? Give it the residual vector. That's just the name of your residual function. And I'm gonna give it the two roots. We said -1 and -3. Done. Done, done, done. Look at that. It gave us -1.46 and -4.28. Okay, so do you think that's consistent with this root? Yeah, -1.4 and -4 point something. Okay, all right, let's attempt this root. So for this root, I'm going to go for x -3, and y, I'm going to try 5. So for x, I'm going to go -3 for my guess, for y 5. And it found -3.3 and 5.0. Perfect, right? There's a root at 0, 0. So if we do 0.1 and -0.1, it's going to find the root 0, 0. And for this one, I'm going to pick, for this last root, I'm going to pick 2 and 1. Okay, let's pick 2 and 1. There you go. Pretty simple and nice. But what the heck is going on behind the scenes? That's what you're here to learn. Okay. Now, in life, in reality, you're just going to use fsolve. Okay. And I know you might be saying, why are we learning this? Because, you know, that skill of trying to push yourself to see the math behind the scenes, I bet you it's teaching you something. You might never have to do that ever again, but there's going to be a problem where you're going to say, oh, I'm going to need to do a multi-dimensional Taylor series and use a Jacobian. that's the objective of doing these things, because you are engineers. Okay, you're not. If I stopped here, then you'd just be using the tool as a technician, and that's fine. But you're here to get an engineering degree, so we need to dig a little bit deeper. Okay. All right. If everyone is done with the programming, no questions, then we switch to the slides. All good on Zoom? All right, my battery is starting to die over here, so I'm going to switch batteries. I don't know why this thing uses so much power. It's like every time I have to burn through a set of AA batteries. Okay, can you hear me on Zoom okay? Thanks, Sovit. Okay. All right, so we are gonna switch back, okay, over here. And now we're gonna go back to the theory. The next step in Newton's method is write out the Taylor series, okay, of the residual function, like we did for the 1D case. And just a point of interest, the other day, I was like, I forgot Taylor's. I actually never knew Taylor's first name. His first name is Brooke. And so, yeah, so we have our own Brooke over here. So, she might be the next mathematician who discovers something big. So anyway, just a little anecdote. All right, so Taylor series, we're going to do Taylor series, but now we have more than one variable, right? So we have x and y, or x and y and z, or x1, x2, x3, xn, right? So we need to expand that in as many for as many variables as is necessary. Now this is the recipe for the Taylor series with two variables, x, y, okay, around point x0, y0. Now remember, last time we just expanded that function, or the residual function, around the initial guess, right, around x0. And then we knocked out all the higher order terms. We truncated them. That's why I'm putting 3 dots over here. I'm only stopping at the first derivative. Okay, and then we set it equal to 0. Now we're doing it for 2 dimensions. You have x0, x, and y. So you get 2 terms for the first derivative, right? X minus x0 df dx, and y minus y0 df dy. If you had 3 variables, you would get x minus x0 df dx, y minus y0 df dy, z minus z0 df by dz, and so on. Okay, I put the 3 dots here because I know we're going to truncate from over here. So we're going to apply the same strategy that we did for the 1D case. All right, so now your job is to take a system of 2 nonlinear equations, R1 and R2, okay, with variables x and y, independent variables x and y, and go ahead and just write this Taylor series that I wrote up there. Okay, for 2 functions, R1 and R2. You're going to get 2 Taylor series, okay? 1 for each residual function. 1 Taylor series for R1, 1 Taylor series for R2. Go ahead and exercise your hands to write the multidimensional Taylor series. Stop at the first derivative. So no, don't do the second derivatives. Just put 3 dots, okay? And you can work in groups. So just do it for R1 and R2. R1 and R2 are just some arbitrary, some dummy nonlinear residual functions, okay? I want you to express R1 of xy as a Taylor series and R2 of xy as a Taylor series, okay? The procedure will be the same if you had more residual functions. And the recipe for the Taylor series is up there, okay? You don't have to substitute the example we did. So this is for general. So don't use so don't use the example that we just did. Just use arbitrary R1 of xy is R1 of x0, y0, and so on. Do it also for another R2. Don't use the example that we did in class, okay? Because we are after the general form now of how this works, okay? So essentially just replicate the recipe up there, replace F with R1 and R2, okay? Okay, looks like most of you are done. I'll show you the answer. It's just simply taking that recipe up there and substituting F with R1 and then R2. We get a Taylor series for each of the residual functions. If you had 1,000 residual functions, you're going to get 1,000 of those, okay? You're going to have 1,000 derivatives over here, okay? And so you see R1 at arbitrary xy is R1 at x0, y0, which is going to be our initial guess, plus this distance, okay? So you're moving in the direction of the gradient, dr1, drx, and dr1, dry, okay? Plus a bunch of other terms, okay? Eventually, we're going to truncate those terms. Okay, so what do we do next? Now, recall Newton's method for a single variable. We first wrote the full Taylor series, and then we truncated by taking the first two terms only, right? So we truncated the second derivative and onwards so that we could have fx, fx0, and x minus x0, f prime. And then we said, okay, this is an approximation to the function. And our objective is to find the value of x that makes f of x equal to 0. So why not set that approximation to 0, that little formula? Okay, so we set that equal to 0, and then we solve for x. Okay, that's why we neglected the higher order terms, because the higher order terms have x squared and x cubed, etc. We don't want to deal with that. With this first term, we can just simply pull x out. That makes f of x equal 0. Okay, and that gave us the recipe for Newton's method. The new value of our root, the improved value of our root, is our previous value, starting from the initial s, minus f at x0 over f prime at x0. Okay, so we're going to do the same here now, except that we are in 2 dimensions. Okay, so these are now, you have 2 Taylor series with 2 variables. Okay. And these are the higher order terms, the f double prime, etc. Okay, so now do the same thing that we did for the 1D method and come up with a system of equations that I claim is going to be linear, that is going to give us x and y. Always, always we go back to systems of linear equations. Remember when I told you during regression, when we did the nonlinear regression, that eventually we're going to turn the nonlinear system of equations for regression into a system of linear equations. Okay. So now do the same thing we did. Truncate the higher order terms, set equal to 0, and find me a solution. Find me a recipe for the solution. So your objective is, let me kind of say it in another way. You have x0 and y0. You have r2 and r1 and their derivatives, and you can evaluate them at x0 and y0. Your objective is to find x and y that make both r1 and r2 equal to 0. Okay, just the same way we did with the 1D equation. Our objective was to find x that makes f of x equal to 0. Right? That's what we're after all. Try it. I'm going to walk around and talk with you if you need my help, okay? But I want you to try it. If you're stuck, want to chat, just raise your hand. So here's a hint. You can, it's going to be annoying to extract x and y separately, but it's going to be easier to leave x minus x0 and y minus y0 as one term, okay? So the x minus x0 is really the distance between the new gas and the old gas, right? So it's okay to leave x minus x0 and y minus y0 as just one entity, okay? Call them capital X and capital Y, for example. I want you to try to see that this is a system of linear equations. Truncate, set equal to 0. Yep. Separate what you know from what you do not know, like we always did with systems of equations, right? So as if you're trying to write it in the form AX equal B, matrix times vector equal vector, okay? So think in terms of systems of equations, matrix vectors, right? Think in terms of systems of equations. Yeah. So not going to work when you have dimensions. It's better to, so call x minus x0 one capital, and then separate that into see the system of linear equations, what you know and what you don't know, and then you should be able to write a coefficient matrix times the solution vector equal a right-hand side vector, okay? Because everything in these equations you cannot know, right? You know the derivatives, you know x0, y0, right? The only thing you don't know is x or x minus x0. You don't know that. So that's going to be your unknown. Yeah, so the man. Okay. Good work. Good work. Yeah. Okay. So how can I help? Can I come this side? Okay. So this is not going to help you because yeah, you're kind of trying to do it one at a time. So instead, can I scroll? Yeah. So forget about this. Focus on this. Okay? You set it equal. This is your system of equations, right? You know this and you know that, and move them to the right-hand side. Now these, what do they look like? X times a vector, right? So if you call x minus x0, x and y, x and y, right? And these are the coefficients of the matrix. You know these, right? Because they're derivatives evaluated at x0 and y0, so you know their values, right? The only thing you don't know is x minus x0 and y minus y0. It's kind of misleading to put it x minus x0, but call it capital X and capital Y, okay? So same thing, same comment, yeah. You guys doing okay? Okay. Yes, yes, good work. Good work. Exactly, exactly. Good work. Yes, really cool, right? Need help? Good. Okay. Okay. So, well, what did we do with systems? When we had systems of equations, we kept the unknowns on the left, along with their coefficients on the left-hand side, and we moved everything that we know to the right-hand side. Right? So what do you know here? Yeah, so R1 and R2, you keep them on the right, but this one, there's an unknown in it, which is x minus x0 and y minus y0. So you got to keep those on the left, and that becomes coefficient, which you know the coefficients, dr by dy and dr by dx, right? You know those values. But what you don't know are x minus x0 and y minus y0. So you have, yes, so the coefficient, then that becomes a matrix times your unknown vector, right? Yeah, so this is not going to get you anywhere. You got to think as a system of equations, okay? Think as a system of equations of move everything you know to the right-hand side, everything that's kind of standard term, right? So right, B, that's our B vector, right? And then the left-hand side is going to have this linear combination of coefficients times the unknowns. And your unknowns are x minus x0, that quantity at capital X, and y minus y0, okay? Perfect. Yes, so you put this on the right-hand side. Yep, that's it. Yep, because you know these, right? Yeah, yeah, good work. Okay. Yes, that is the Jacobian. Okay, all right, you guys. So let me help you untangle that. It was a good discussion, talking with you, kind of seeing you all got it. So that's a very good sign. Okay, so the first thing I want to do is truncate the series. So knock out all the 3 dots, and you see how I put an approximation over there. Okay, and the next thing is to set R1 and R2 equal to 0. So now, despite the fact that this is an approximation, now I'm taking the right-hand side and setting it equal to 0. So now I'm switching to equal sign. So from here onwards, this is the system that we're dealing with. Okay, we've neglected where we've discarded the approximation we started with. This is the system we're dealing with. When you look at this system, there's a lot of terms. Okay, but when you think about it, you know x0 and y0 and R1 and R2. So you know this term, R1 at x0, y0, and R2 at x0, y0. You know this. It's just a value. Now, when you look at these 4 terms over here, the only thing you don't know is x and y, or also x minus x0 and y minus y0. This difference, x minus x0 and y minus y0, is simply the distance between your previous guess, x0, and your new guess, x and y. Okay? So now these quantities are multiplied by known values, right? So you know the derivatives of your residual functions, and you know that how you evaluate them at the previous guess. So this is simply a coefficient. So now when you step back and look at this, this is nothing more than ax plus by plus c equals 0, and dx plus ey plus j equals 0. It's 2 equations with 2 unknowns, 2 linear equations with 2 linear unknowns. Okay? So here's what I'm going to do. I'm going to write this in matrix vector form. Okay? If I write it this way, I get these 2 guys as a vector plus the 4 terms over here. This is a matrix times this vector, x minus x0, y minus y0, right? So see, the first equation is dr1 by dx times x minus x0, gives you that term up there. And dr1 by dy times y minus y0 gives you that second term up there. So this is identical to the system above. Okay? You might be tempted, as I saw, to just extract x and y. And that's kind of the annoying thing about this system. But if we let go of that idea and instead search for x minus x0 and y minus y0, then you can write it very, very neatly this way. Okay. Now, when you write it this way, if we define the solution vector, x vector, as the vector x0, y0, or the pair x0, y0, then you can also define this residual vector, which we saw how we define in just a few slides ago, right? When we did it for fsolve, okay? So that's called the residual functions vector. This matrix is a very special matrix. You notice that the first row contains the first residual function, and the second row contains the second residual function. The columns correspond to the derivatives of said residual function with x for the first column with respect to y for the second column. Okay. Now this matrix, we'll see it's generalizable to n nonlinear residual functions. Okay. You'll just have to differentiate x, y, and z, and so on and so forth. First row is first residual function. Second row is second residual function. The columns correspond derivative with respect to the first variable, derivative with respect to the second variable, third variable, and so on. Okay. Now, that solution vector, I'm going to call it delta, because delta is the distance that x minus x0 and y minus y0 is simply the distance between the previous guess and our new guess. We are after delta, like Maxime said. We are after making delta, okay? We are after shrinking delta as we iterate, okay? Until when we reach a point where xk plus 1 minus xk is 0, then we've converged. We're no longer improving our previous guess. Okay? So now when you write it in matrix vector form, it's very clean, okay? Very neat. I do not like systems of equations. I like matrix vector form, okay? So when you write it in this form, you have Rx0 plus Jacobian J. I put x0 over here because J is contains numbers. It's those derivatives evaluated at the previous guess times delta. Delta is the distance between the new guess and the previous guess. Our objective now is to solve for delta. So you write it as J delta equal minus R. And now we can just invert this by saying delta is simply minus J inverse R of x0. And that's how you solve a system of nonlinear equations. You solve this and you repeat. So start with x0. You solve this, you get x1. Put x1 back in here and solve it to get x2. And keep solving until the distance between the k plus 1 guess and the kth guess, this delta, becomes negligibly small or less than a tolerance. Okay? So now I want you to compare this formula to the 1D case. In 1D, we had x equal x0 minus r over r prime, correct? Or x minus x0, which is delta. Okay, so that's delta. Minus, you have a minus. R of x0, that's r of x0. Here we have 1 over r prime. Over here, we have J inverse. Now, J contains derivatives. For one dimension, the Jacobian matrix is simply r prime. And the inverse of r prime is 1 over r prime. But in multi-dimensions, 1 over r prime is J inverse. Right? So you see the analogy between the multi-dimensional case and the 1T case. I find that strikingly beautiful, but you know, it gets heart palpitations when I see this kind of level of beauty, how beautiful mathematics is and consistent it is. Anyway, okay, now more generally, this is how we write this. We say that the Jacobian, this is the system we're solving. Jacobian evaluated at the kth iteration, okay? So what you know, times delta is equal minus r, the residual vector at the kth iteration. And delta is the difference between your k plus 1, this is what you're after, okay, minus the previous iteration. So you solve for delta, and you know xk, so you can get xk plus 1 out of it, okay? So fairly easy. And this is the algorithm, just like before. Given a residual vector and an initial guess and your Jacobian, okay? You calculate the Jacobian at x0, and you calculate r of x0. You invert, calculate delta by taking the inverse of j times r, and then update the roots or check for convergence or check if delta is small enough. That means you're not improving. Your computer is not, excuse me, able to improve much anymore, okay? Okay. So if we go back to this system, the example that we were working with, the critical step in doing this by hand, or if you're programming it, is to define the Jacobian, okay? The Jacobian, again, first row contains the first residual function and its derivatives with respect to the first variable, the second variable, and so on. And for the second row, you have the second residual function, R2, differentiated with respect to x and y. So this is what you get here. dr1 by dx is 3 over 2x squared, okay, minus 4. Okay. dr1 by dy is 1, because y is 1 times y, right? And r2, you have dr2 by dx. So you have to do kind of this derivative of the sum over here. You get minus e to the minus x cosine x and plus e to the minus x sine x, and dr2 by dy is 1. So that's your Jacobian. Now you know your Jacobian, okay? And this is an example by hand. So if we were to start with an initial guess, x equal minus 2 and y equal minus 4, then you would calculate j and r. So you take x equal minus 2 and y equal minus 4. You plug them into the matrix for j. You evaluate the values. This is what you get for j, and this is what you get for r. I mean, it's just substitution and calculation. Clearly, we're not going to do this by hand. In practice, we're going to program this next in Python, okay? Then you solve for delta. You invert it. I used a calculator to invert this. And then you update. So that gives you delta. That's the distance between x1 and x0 and y1 and y0. So y1 is delta plus y0, and x1 is delta plus y0. So this is what you get for x1 and y1, and then you repeat, okay? So you keep repeating until you converge, okay? So this is an example by hand, all right. Okay, so let's go ahead and do this in Python, okay? Together in Python. So we already have our residual function, residual vector defined, correct? We already have that defined. Now we need to define our Jacobian. Actually, I think I might switch to the slides. Give me a minute. Actually, let me go through this slide first. Okay, so before putting this on a computer, formulate everything by hand. Okay, write your Jacobian by hand, write your residual functions by hand, make sure everything is clean, okay, so that you can translate them directly on your computer. Okay, now think also about what tolerance you want to use and what initial guesses you want to use. Could be a hint from a graph, for example, or some other intuition about the system that you're solving. And if you can do a few iterations by hand, that's great. If not, carry on to Python. You need a function to calculate the residual r of x, and that should take only one argument, which is the vector of x values, okay? if using an analytic Jacobian or the Jacobian by hand. We will talk about the numerical Jacobian later, what that means. But if you have the Jacobian, you need to write a function that calculates the Jacobian as a matrix. So this is what we did right now. Okay, this is what we're going to do now. And finally, you write your Newton solver as a function. It should take the following arguments: the function name or the residual name, the Jacobian residual, initial guesses, and a tolerance. That's at a minimum what your Newton solver is going to need. It's identical to what we did last time. We took a residual function, an initial guess, okay, maybe a number of iterations, okay. We also gave it a derivative, right, last time. There was an option where we did a numerical derivative. We'll see that because you can do the Jacobian with a numerical derivative as well. And finally, a solution tolerance, okay. And I'll show you here a couple of examples, what this looks like. So for this example, this is your Jacobian. You just return it as an array. I like to use NumPy array applied to a bunch of lists because they're very clean, okay, very clearly displaced. First row, second row, first column, second column, okay. And this is your residual function that we just defined. So that's all. That's the only other function that we're going to need. And we clearly need a Newton solver routine for multiple dimensions, okay. All right, so let's go ahead and do this together. Let's see. I'm hoping to, so when we do this kind of sometimes without like any guideline, I make errors, which is good because then we can discuss those errors together and, you can correct me and I can revise my thinking and you'll see how I'm thinking about it. So I'm going to define define Jacobian for this system, whatever you want to call it. That Jacobian also takes an X vector, X vals. Okay, so in this case, we have, so I'm going to take X as X vals 0 and Y equal Y vals 0. You know what I'm going to do? I'm going to move this and put it up there. I'm going to move it and put it next to our residuals vector. Okay. Okay. And for the Jacobian, I'm going to return an numpy.array. Okay, I'm going to nest a list of lists over here. You might do it in another way. That's fine. Okay. So we have 1.5 times x squared, correct? Minus 4. And then we had 1. And then for the second row, we had minus cosine x times exp of minus x plus sine x times exp minus x. And then 1. Okay. So the Jacobian, when we are doing the Newton solve, we're going to call the Jacobian and give it our guess, our previous guess. And it's going to come here and evaluate, plug in x and y, and evaluate and return a matrix. And then we're going to invert that matrix, okay? Okay. We all synchronized? Perfect. So now let's define our Newton solver. Newton solver. So we said our Newton solver is going to take a residual function, and it's going to take a Jacobian function too. And it needs an initial guess, x guess as a vector, and a tolerance. Okay. All right, so let's see, how do we go about this? We can start with a, okay, so what are we gonna need? We're gonna need, okay, so here's a cool thing. If I give this So if I call this function, this function, residual function, that's a vector valued function that takes a vector valued argument. So if I call residual function on x guess, it's going to give me an array. Agreed? It's going to give me 2 values in this case, or whatever values. This is generic. This is a generic solver. Okay. So first, I'm going to evaluate my residual function. I'm going to call it f value. I'm going to evaluate it at, or let me call r value. I'm going to evaluate the residual function at my x guess. Okay. And from that, I can now define an error. Okay. Can define my error now as the norm of that value. What if my initial guess was so good, right, that it produced an error less than the tolerance? And my error here, my initial definition of the error is going to be an absolute error. So essentially plug in x and y into the residual function. If it makes them 0, great, we found the root. Because you're always holding accountable your residual function, how close it is to 0, right? So now R value, wait, it went down. So R value contains the effect of x guess on the residual function. So if x guess is a root, R value is going to be almost 0. So I'm going to take the norm of R value to define my initial error. Okay, that makes sense? R value has, in this case, 2 values in it. So how do we define errors for a vector? We take their norms, right? So that's what I'm going to do. I'm going to take the norm, okay, mp.linalgebra.norm of R value, and I'm going to take the L2 norm, okay? Now, just like we did last time, we needed an iteration counter. We also wanted to stop at a maximum number of iterations. And we said that we did a while loop last time. As long as, or while, the absolute value of my error is greater than the tolerance, so as long as my error is worse than the tolerance, and my number of iterations is less than, I don't know, do 300 iterations, then let's solve our system of equations. So for our system of equations, we need the Jacobian matrix. We need to invert the Jacobian matrix, okay? So J value is simply Jacobian function, okay, at x. So let me do something here. Because I don't want to call everything x guess. I'm going to call and declare a new variable x and call it and initialize it with x guess, because I'm going to keep updating this x as we move on. Okay. I don't want to call it x guess. It wouldn't matter, but I don't want to call it x guess because I want to distinguish this x guess from what we're computing internally. Okay. So that gives me this J value is a matrix. Okay. That's the Jacobian matrix, right? Look at this. If we had passed on, call this, let's say, Jacobian for class example, okay? Class example. If we had passed this Jacobian and gave it an x value, x vector, is going to return a matrix. Agreed? So that J value is actually my coefficient matrix. And it's coming in with an x0 now, okay? That's my guess. So now I have the Jacobian and I have the right-hand side. So now I can simply solve for delta. Delta is equal mp.linalgebra.solve. I'm going to use the solve. I'm going to give it my coefficient matrix, which is J value. And my right-hand side is minus R value. So remember when we did linear systems, let me show you the slides. That's what we're solving. J times delta equal minus R. And you use numpy.linalgebra.solve. You give it your coefficient matrix, and you give it your right-hand side. That's what we did there. Okay? Okay, so that gives us delta. Now we can evaluate, so that is solve. Solve for delta. Now finally update the roots. So my new x now is equal my old x plus delta, right? Because delta was defined as xk plus 1 minus xk. So xk plus 1 is xk plus delta. But we do it here with a simple swap. New x equal old x plus delta, or xk plus 1 equal xk plus delta. That is what this equation does. Okay, this is not an algebraic math where you can cancel out x and x. No, it's saying new value in the memory that stores x is equal to the old value in the memory of x plus whatever is in delta. Now we can update our error. We do f r value. That's our new r value is residual function evaluated at the new x. Okay, and now we update our error. It's mp.linalgebra.norm r value L2 norm, and I increase my counter. Okay. Finally, once I'm done, return x, number of iterations, and the error. Now, you can do an error checking. We'll do it later. Don't worry about it now, but that's it. So that's it. Like, what are you talking about? That's it. Easy for you to say. I know. Okay. So let me prove to you that this works. Let's see if it works first. Okay. Whoa. In my where? This one here. Yes, thank you. Thanks. Good catch. Thank you. Okay. So this is what fsolve gave us. Let's try to do it with our Newton solver. All right, with our Newton solver, we're going to give it the residual vector. That's kind of the function. And we're going to give it a Jacobian for class example. And we're going to give it an initial guess -1 and -3. And we're going to give it a tolerance of 1e to the -5. Oh, it's through an error. Very nice. Okay. Name y vowels is not defined. Why do I have y vowels? Pardon me? Excuse me? Oh, x vowels. Thank you. Thank you. Thank you. Pardon me? Oh, yes, x vowels of 1. Love it. Okay. Oh, look at that. Yeah. 4 iterations and our solver converged to the one that fsolve returned. I was telling some of you during the research fair, like this is what I love programming, because you get immediate results for either how bad you screwed up or how well your code is working and how to fix it. We can try with the other roots as well. So Newton solver. Okay, so let's give it this -3 and 5. Look at that, perfect. Okay, I see some puzzled faces. Please raise your hand. I'm here to help you, maybe. Hey, Paula.
Shouldn't have a zero vector somewhere?
Pardon me?
Because I get that answer and then I get something different here. And this is Jacobian, the one that you did for class. Like both of them are negative.
So let's go to the Newton solver. Your Newton solver. Your Jacobian looks like it's correct. Yep, for Newton solver. J value. Error and iteration. Tolerance. And minus R value. No, you gotta return outside the while. So here you've returned the first iteration. Okay.
Yeah.
All right. You got it, Maxime? Okay.
I have no idea what that is. Another plus.
So this is increasing my iteration counter. So you have to your indentation is all wrong.
Oh.
Yeah, so this is not going to do anything. And you need a semicolon colon over here. Yep, and you have to indent everything inside the while loop like I'm doing. So let me scroll that up a little bit.
Okay.
This n iter plus equal 1, it increments. We need to increase our counter. So we're counting how many iterations we're doing. This is saying n iteration equal n iteration plus 1. It's a shorthand.
Is it more like simple and show that my whole formula is increasing?
Yeah, so I'm just adding 1 to my counter. N iter is a variable that counts my number of iterations. This n iter plus equal 1 means add 1 to number of iterations. That's what it means.
Oh,
It's just it means add 1. Okay, yeah, but you got to fix your indentation.
Got it. Thank you.
Cameron.
Oh, I don't know if you changed something in your code, but I've just been getting an error with the Newton solver.
Reference, so scroll up. So yeah, when you read your error, you have not defined error over here yet.
Oh, I see.
Right. So yeah, if you scroll down and you see it tells you local variable error reference before assignment. So if you scroll back here, you're saying while absolute value of error, but it's saying, wow, what is error, right? So you gotta that's error. That's our initial error. So you gotta declare that over there. Yes, let me scroll back up one and I'll come back here. Bad, do you mind? Bad operand type for unary minus. So that's coming from here. Cosine, yeah. So you're missing a cosine x. Okay, so let's start there. Looks like, oh, you're off. Your answers are off, right? Yeah. Okay. So your Jacobian is off, is wrong. Yeah, it's missing a sign, it's missing plus sine x e to the minus x. Yeah. On Zoom, you all doing okay?
Yeah, Professor.
Perfect. All right, so I still have 5 minutes. Still have 5 minutes. I want to finish off this chapter. Okay. I have another example here for you, which is the intersection of a circle and some other function. Okay. That's just one other example trying to find the intersection points. Go ahead and implement it in the code we just did. And this is, again, Jacobian and residual form. Okay. And that's just kind of one more example to exercise the code we just did. Okay. Now, in general, the same strategy applies for n residual functions and n unknowns. Could be a million of those, or 5, okay, or 17. It doesn't matter. Okay. So, or 11. Okay. My son, every time I drop him off at school, before I go, he's like, "Poppy, 11 hugs." And I'm like, why 11 hugs? You know, beats me. It's anyway, it's funny. So I like that number. So even if you had 11 equations, okay, same thing, you get the same system, except now your Jacobian matrix is gonna grow accordingly. Okay. Now notice for n residual functions and n unknowns, you're gonna get an n by n Jacobian matrix. Okay. In the first row, you get the first residual function R1, second row, second residual function, all the way to the nth residual function. Now, our independent variables here are x. I call them x1, x2, xn, because you run out of alphabet, right? So that's the x, y, and z, etc. So you differentiate with respect to x1 in the first column, with respect to x2 in the second column, and so on all the way to xn. Okay. And the same system, exactly the same. 2 equations or 1,000 or 11, j delta equal minus r, and you solve for delta. Okay. So our Newton solver that we just wrote should work for an arbitrary number of equations. And that's kind of what's behind the scenes in Python. Okay. Fsolve. Okay. This matrix is very special. It's called the Jacobian. It kind of characterizes the slopes or the derivatives, the rates of change of all of these functions as you're moving in multiple dimensions to try to descend or ascend to the root. Okay, that's what this does. Okay, that Jacobian. There's one more item of discussion that is worth talking about. Sometimes it is very annoying to do an analytical derivative when you have 1,000 equations or 11. Okay, it's very annoying. So what we often opt to do is do finite differences, just like we did with the one-dimensional case derivative. You can use forward, backward on central differencing, but you have to fill out the entire Jacobian with finite difference approximations. Okay, so you got to find your way around, okay, each point in the Jacobian and do a finite difference with respect to the derivative, with respect to the variable you're differentiating with. So if you're differentiating with respect to x1, you do residual function of x vector plus x vector plus delta x1, okay, or whatever that delta is, okay, that small value, and you define those derivatives and you apply them across your entire Jacobian, okay, numerically. Okay, we don't have to do that here, but just, as an FYI, that's what fsolve does internally. With fsolve, you can also provide it with an analytical Jacobian, okay, that often gives you better accuracy. But if you don't have an analytical Jacobian, you evaluate a numerical Jacobian, okay? And that concludes our chapter on nonlinear solvers. On Thursday, we will start on ordinary differential equations, our last chapter for the season, okay? Thank you so much, and I'll see you on Thursday. I'll assign your homework on Thursday as well, okay? Thank you.
Does that mean our homework 8 will be due next Thursday?
Yes, Matt.
Okay.
I'll try to assign it sooner, but I have to update a few things. I might not be able to do it on time. So.
Okay, no problem.